Functional dependencies are the heart of database design process. It's vital to understand them. In this video, we will first introduce FD. FD is an acronym of functional dependency in general terms, and introduce a couple of notations. Then we will go over an example together. In the end, you will do a self-check question. Let's get started. First, what is FD? An FD occurs when the value of one set of attributes A can determine the value of a second set of attributes B. We can write this FD as A to B. Here, this right arrow represents determines. So you can read this FD in two ways. You can say A determines B, or you can read B is functionally dependent on A. Here, A is determinant. Okay. And always remember, FD is a context specific because for a given sample data, we discover one or more FDs. It's always based on the sample data, based on assumptions from this sample data. It doesn't guarantee that we will be able to discover the same FD from a different set of data sample. Okay, so this is the context specific. Every time when you specify FD, you should give the assumptions to support this FD. According to the previous definition, still, it's not that easy for us to discover all the FDs from a given data set. What about this one? With this interpretation, it's pretty easy for us to discover the FDs. In a given relation R has three attributes, A, B, and C. This is an observation from a simple data of relation R. For any two of tuples, tuple is just rows. For any of two rows, T and P, if T and P have the same value for A, they must have the same value for B. Okay. According to this condition, we can claim we have a function dependence, which is A determines B. Okay. So now let's apply this to discover functional dependency. Before we do discovering, let's look at these two function dependencies to see if we can understand why this is a functional dependence between these two sets of attributes. Let's look at the first one. The first one is student ID determines student name. So here, it means if we know the value of student ID, that means we can also know the value of student name. Okay, so this is what the function dependence tells us. However, if we try to apply this condition to this functional dependence, that means if we have two students, T and P, two students, then this function dependence tells us if these two students, they have the same ID, T dot student ID equal to P dot student ID, then we know T and P, they must have the same name. So let's say, as you know, student ID should be always unique, which means there's no two students they will have the same ID. But just assuming we do have two students, they have the same ID, they must have the same name, which actually they are the same person. Okay, so this is definitely is a FD. It's true, right? So also at the same time, sometimes if we have some unique identification number such as the student ID, this ID attribute sometimes is very likely to become a determinant in one or more FDs. Okay. So let's check the second one. Second one is student ID section number to grade. So this is also some cases you will see very often. Assuming you have a transcript. On the transcript, you have a number of grades, each grade from one class, specifically from a class section. If a class has multiple sections, here that's why we say section number. Class name may not be able to determine your grade along with the student ID. Okay, so here we just specify is a section number. Section number with the student ID together, this set of attributes can determine a grade. This grade is one grade specific with your ID and one section on your transcript, which makes sense to you, right? So this is FD is true. Okay. So this one implies if we have two rows or two students, these two students, they have the same value for the set A. Set A is the determinant on the left-hand side of the function dependence. If they have the same value for both student ID and section number, they must have the same grade. So again, the same as the first ID. If two students have the same ID, they must have the same students. Okay. So this is the example of functional dependencies. And also you noticed in the second FD, we have a set of attributes, not just a single attribute like the one in the first function dependence. We call this determinant as a composite. Because it contains more than one attribute. This is just a term in FD. Okay, next we also have another kind of functional dependence. This is a multi-valued functional dependence. What is multi-valued? That means a determinant can decide a set of value for the second set of attributes. Okay, let's check an example. We have two examples here. The first one says employee determines degree, and this FD is multi-valued. Because you see, some people they do have more than one degree, right? They have a double major, or they have a bachelor degree. They also have a graduate degree. So this is makes multi-valued functional dependence. Okay. The second, a student can join more than one club. So if two students they have the same student ID or some other identification number, then they must have the same value for their club membership. However, because here each determinant, they may have the multiple values for the attribute set on the right-hand side. So this is a multi-valued functional dependence. Okay, so next let's check a number of properties with a functional dependence. Assuming here we have three sets of attributes, A and B and C. Okay, their sets. They may only contain one attribute, but they can also contain multiple attributes. So that's why we say three sets of attributes. We also use this letter, uppercase letter, to represent set instead of single value. A, B, and C. Okay. The first property is reflexibility. So this means if B is a subset of A, then A can always determine B. So, which makes sense because a set can determine itself. And of course, to determine a smaller set, a subset of itself. So this is reflexibility. The second one is augmentation. Augmentation is you can append the same set of attributes to both sides of functional dependence. For example, we just add C this into both sides of functional dependence. Then we still have this functional dependence is true after adding C to both sides. Then we have AC to BC. Okay. Again, this is the same. C can determine himself. And the next one is decomposition. It says if A can determine B and C, here B and C makes a new set. Okay. Then we can say A can determine a subset of B and C. So B and C, both of them is a subset of the union of B and C, right? So we can say we can decompose this original FD into two FDs. One is A to B, the other second one is A to C. Okay. So this one actually from the first property, reflexibility. A set can determine a subset. Okay. Then the next one is transitivity. Transitivity, that means we can transfer FDs from first one to the next one. Here it says A to B and B to C. With these two FDs, now you can transfer this FD from A to C. So because B can determine C, B is determined by A, so A can determine C. This is the transitivity. And however, this transitivity, they are not true. Okay, they are not true conversely. So we cannot say if AB determines C, the union of A and B together determines C. Then we can never say A can determine C, B can determine C. It's not sufficient. We have to use both of them can determine C. Okay, so this is the some properties with FD. When do we use these properties? In the relational data model, it's based on the relational algebra. So we actually apply this FD and these properties to discover the primary key for a relation. Okay, what is a primary key? In theory, a primary key is a set of attributes which can determine every attribute in the relation. This set, it is a primary key. Okay, then the primary key in relational algebra is a closure. Closure of a set of A is the smallest closed set containing A. Okay, so this is a little bit abstract because that's a algebra. Relational algebra. However, the second one gives you some informal definition of the primary key used in relational database. The first one is used in the relational algebra, but the closure of a set A, it is the primary key for the relation containing A. Okay, so such a set, such a closure makes a candidate key in a relation from A, but we can select candidate keys. select one of these candidate key as a primary key. Okay. So next, let's just try do this just for fun, because we will not do this in the relational database class. However, I think that's interesting to do this. So let's say given a relation containing A, B, C, D, E, these 5 attributes. Here I use this uppercase letter. You can also use lowercase letter, but if I use uppercase letter, just means these letters could be a set, but could be a single attribute. Okay. And we have discovered in this relation, we have 2 FDs. We write here, one is A to B, the other is AC to D. Okay. With these 2 FD function dependence rules, can you find a closure that determines A, B, C, D, E, the whole set of attributes? Here, actually, we can apply the these properties from the previous slide. So let's do this just for fun, okay? So when you do this discovery of the closure, the smallest attribute set can determine every other attribute, the set of attribute, the entire set of attributes. We always start from the longest functional dependence. What's it mean? What we mean when we say longest functional dependence? The dependence containing the most attributes. Now let's look at these 2 FDs. Which one is longer? Of course, the second one, it contains 3 attributes. So we will start from this longest functional dependence. Okay, so if we write here, let's say, okay, so this is longest functional dependence. Now, the target here, we want to add more attributes, new attributes into this side, right-hand side, until this becomes the entire set of attributes, until we see A, B, C, D, E, all the attributes appearing on the right-hand side. Okay, so now we will start use augmentation. Okay, augmentation. What's augmentation? Let's try. Augmentation is if A to B, then AC to BC. Okay. Then we just add AC. Okay. So if I add AC here, AC and AC union, this still just use it because a set doesn't contain duplicates rows. All the values in the set is unique. So we can add AC on the right-hand side, but if you add AC to the left-hand side, it's just redundant. We can get rid of that. So AC on the right-hand side, so this is still true, okay, according to the augmentation. Then next, let's see, we can apply the second one, A to B here. Then A, okay, we do have A here on the left-hand side. So A can determine B. Now we can write B here. Okay, so now we already get 4 attributes here. We're only missing the last one, E. Okay, now we can check these 2 function dependencies. Do we have E in either of this? No, we don't have E. So that means nobody can determine E. E is independent in this relation. So then we have to add E on both sides. Then we have all the 5 attributes on the right-hand side. So this ACE makes the smallest attribute set, which can determine all the attributes in the relation. So this is the closure. This can also become a primary key in the relation R. Okay, so this is the use of closure and properties of functional dependence. Now let's continue. So this is an example. Let's discover all the functional dependence from this sample data. You are familiar with this sample table. We have practiced the SQL statements according to this skill data. This is a skill data table. So let's look at this table. The table contains 4 columns, or we can say 4 attributes. Okay. We have skill. You know, skill is a stock keeping unit, which is a unique identification number. Okay, then you must pay attention to this kind of attributes, especially is unique. Then the next one is a skill description. Then department and bio. Recall the previous explanation about FD. We have applied this condition. If we have 2 rows, T and P, then if TA equal to TP, TA equal to PA, okay. And TB equal to PB. This is the observation. Then we can specify we have this functional dependence A to B. Okay. Now let's say, do we have any 2 attributes? They meet this condition. Let's look at here. We do have a department and a bio. You notice these 2 columns contains many identical values, same values. So let's check department. We can see department, the first 4 rows, they all have the same value for the department. And also for the bio, we have first 2 rows, then row 3, row 4, then all these 4 pairs of rows, they have the same value for the bio. Okay, so now we could possibly discover some function dependencies from these 2 columns. So let's check. First, let's see if we try to find if any dependence between department and bio. So let's see, that means if 2 rows, they have the same value, same department, do they have the same bio? This is the condition you need to check in order to determine if this FD is true. So if you want to say if department can determine bio, then the condition should be if 2 rows have the same department, do they have the same bio? We just we do this only based on this 8 sample data. Okay, only according to this 8 sample data do we have this condition. So let's see. The first 2 rows, they do have the same department and the same bio as well. However, this doesn't take place for the row 2 and row 3. You can see row 2 and row 3. So if we check row 2 and row 3, they do have the same department. However, they have the different bio. Okay, so now we can see this FD. No, it's not true. Okay. Then we can check if this FD is true. Conversely, so can bio determine department? Okay. Now we can check the condition. Do we have any two rows having the same bio? We do. We have check the last column bio. We have 4 pairs of rows. They all have the same bio. Okay, let's check. Row 1, row 2, they do have the same bio. Okay, they also have the same department. Then row 3, row 4. Okay, same bio, same department. Then 5, 6. Yes. Then 7, 8. Okay, same bio, same department. Okay, this condition is true. All these 8 sample rows, they meet these conditions. Then according to this sample data, we will say, yes, this is true. Okay, this is the FD. We just find the first FD here. Okay, then let's continue looking for any other function dependence. Let's check. Since bio can determine department, can bio determine other attributes? Can bio determine a skill description or skill? Let's say. Now, very easy. You can say same bio they have different skill, and same bio they have different skill description. For example, for the Cindy Low, they have the same bio for the 5 and 6 in these 2 rows. However, 5 and 6 they have the different skill description. So now bio can only determine departments. Okay, so now let's check skill and skill description. Okay, so now let's check skill and skill description. Can skill determine some attributes? Let's see, skill here is unique. So if a skill is unique, then it's very possible to become a determinant. And in most cases, a unique identification is a primary key which can determine every other attribute. Is that true for these 8 sample rows? Is this true? So let's say the skill is here. The skill, we have all the skill, they're unique, right? And if the skill is unique, that means if we do have 2 rows, they have the same skill, they must have the same skill description. However, in this case, it's unique. So skill determines the skill description, department, and the bio. There's no duplicates. So actually, we should have this second function dependencies, skill, and determine all the other attributes in this relation. Okay. And let's see, skill description. Can skill description determines anything else? So let's check. Do we have any two rows that have the same skill description? No. For these sample rows, we don't have. It looks like a skill description is also unique, just like a skill number. Then in that case, the skill description may also determine skill, department, and bio. Okay. However, when we specify the primary key, we have a rule about primary key. The primary key we prefer numbers than a string, so that's why we choose a skill number instead of a skill description as a primary key. However, the skill description it is a determinant. Can determine all the other attributes. So we do have this three sets of function dependencies discovered from this skill data. Okay, so now let's check this is the solution. It is exactly the same as what we have discovered previously. Okay. So the last one is a question. You can do it as a self-flow check. This question is from the slide 37. The discussion in this video based on the slide number 28. Based on the slide number 28 to 37. Okay. So this is the exercise you can find on the slide 37. Here, I will not explain this self-check question. Please do it yourself, but I will discuss this exercise with you together some other time. Okay.